Good evening, everybody. Good evening. The disco music has gone off now. Thank you. Oh, yeah, I forgot about these lights. So, welcome everybody to the 2025 Glossop Medal Lecture and Glossop Award. Welcome to those in the room. Fantastic turnout, which is excellent to see so many of you. And thank you very much to those joining online as well. Welcome to you. I'm Anna Morley. I'm the current chair of the engineering group of the Geological Society. As you know, we're here in the historic Royal Institution, which is just a short walk from the Geological Society, where many of us have been just enjoying the first Fuchs meeting for engineering geology, which was day one today, day two tomorrow, and that was great and thoroughly enjoyable for me. Just a reminder to turn your mobiles off, please. There are no fire alarms planned, so if there is a fire alarm, it is real, and the exits are there and up there. Great for our speakers to make a speedy exit. And I'm told that you have to meet at Sir Winston, so that means you go right out the doors, right again, and Sir Winston is there on the bench. I'd like to welcome Emma Slack and family, who are fantastic supporters, Rudolph Glossop's daughter, fantastic supporters of eggs over the years. So welcome, Emma. And I would also like to welcome our 2025 Glossop lecturer, Dr. David Giles, and his family. And finally, I would like to welcome Chris Spence, our Glossop Award winner, and his family, and I would like to invite you, Chris, up to the lectern to give your lecture. Thank you very much.
Good evening. My name is Chris Spence, and I'm here today to talk about the importance of geological insight to nuclear development, with a particular focus on my experiences at Hinkley Point C. Today my talk is going to be split into two halves, with the first half going to be focusing on an overview of Hinkley Point C and its regional geological context, and then in the second half I'll be talking about my personal experiences at the project. So, Hinkley Point C is the first new nuclear power station to be built in the UK in the last 30 years, and when it's completed will be the first nuclear qualified safe structure in the UK. Once operational, it will provide low carbon power for 6 million homes, which is the equivalent of London and the southwest of England simultaneously. So the importance of the nuclear industry is growing, with in 2050, 25% of the projected electrical demands will be fulfilled by nuclear. So the importance of geological insight for nuclear-rated structures, amongst many things, I've focused on planning and construction. When planning and locating nuclear sites, we must consider seismic resilience to near and distal ground movements, as well as the effect of liquefaction, climate change adaptation with changing sea levels and coastal erosion processes, and then ongoing geological processes such as slope stability issues on land and in marine environments, as well as dissolution in some places. During construction, we have to look at unexpected ground conditions and mitigating those, working in a corrosive environment at the coast, and then the normal tunnelling and underground structural hazards as well. So, during my involvement at Hinkley Point C, I was involved in the marine works, and the purpose of the marine works was to transport seawater from the Bristol Channel through to the nuclear power station, where it was circulated around the reactors to cool them down. The water is then treated and then put back out to the Bristol Channel. This is done by 3 tunnels. We have 2 intake tunnels, which were 3.5 kilometres long and 7 metres in diameter. And then we had the outfall tunnel, which was 1.8 kilometres long and 7 metres in diameter. At the distal end of these tunnels, we had 2 shafts which connected to the seabed. And the tunnels themselves were sunk by TBM, the shafts sunk from offshore vessels. And then we have where I was involved, which is the tunnel shaft connections. Something I think is quite interesting about these tunnels is when they are in full bore and operational, they'll be able to transport 120,000 litres of water per second. And something I quite enjoyed was the fact that they were predominantly gravity driven, with a nod to efficiency there in order to reduce the amount of pumping and therefore the cost of producing a unit of electricity at the power plant. So I'm going to take a closer look at where I was involved in, which was the tunnel shaft connection. So on the left-hand side of this diagram, you're going to see there's the shaft, which connects to the seabed, which is about 12 meters above us. And on the right-hand side of the diagram, you're going to see the TBM tunnel, which connects back to the power station. These two structures are offline from each other to isolate the stresses that they put into the rock during excavation. But this requires a connection between the two. So in my case, I was involved in what was the temporary works, in which we were opening up an underground space driven from the TBM tunnel over to the shaft. This opened up a space, as I say, to allow the permanent solution, which was a reinforced concrete structure, to be assembled within that. So I'm now going to talk a little bit more about the regional geological setting of Hinkley Point C. On the left-hand side of this diagram, you can see a geological map of the Bristol Channel. On the right side, we have a generalised strat column, highlighting some of the key time periods and units. So begin in the Carboniferous, where we have deposition of interbedded limestones and sandstones, and these were heavily deformed during the Variscan orogeny. So we had a compressional tectonic regime resulting in thrusts and normal faulting. Fast forward to the Triassic, and we have a period of extension in which we then have openings of half grabens and deposition of sediments. So in this case, we have the Mercia mudstone, the Ardent sandstone, Blue Anchor Formation, the Penarth group, and then continuing into the Jurassic period, we have continued rifting, and we have deposition of the Blue Lias group, which is what we ended up tunnelling at Hinkley Point C, the Oxford clay, the Kimmeridge clay above that. During the Cretaceous, we have reversal of the tectonic structure setting, and we go back into compression, so we have reactivation of the existing structures in compression. And then following that, we have the deposition of the Quaternary deposits. What they've done for us, I'm not sure yet. So, moving forward, so I'll look a little bit closer at the Jurassic sediments, the Blue Lias Formation. So on the left-hand side here, we have what will be a familiar view to some people. It's at Limport Bay in Wales. And on the right-hand view, a little less popular view, under the Bristol Channel. So the Blue Lias Formation is mudstone and limestone interbeds. The limestone beds are 30 to 300 mil thick in what we've seen, argillaceous and blue-grey in colour. The mudstones are much more thinly laminated, just like this one I rescued. Much more thinly laminated, dark, and in places fossil-rich. So this one I took because it's full of ammonites. And much more fissile as well. So I'm going to talk a little bit about some of the key hazards that we came across while we were tunnelling in this formation. So, as I mentioned, we have variable ground conditions, which resulted in variations in strength over short distances, but also meant we have different rockfall or rock failure mechanisms. So the limestones are much blockier and therefore more liable to kind of kinematic failure types. This was mitigated by additional bolting in places. And then we had the mudstones, which were much more prone to like raveling failures and soft ground squeeze. This meant that these were monitored by, or mitigated by shotcrete and ongoing monitoring. We then have groundwater and ground gas. So associated with the Blue Lias Formation, we have interbeds of organic rich material, which can produce H2S and methane. And then combined with the Bristol Channel above us, this results in the potential for groundwater and ground gas inundation to the adits. We then have the potential, as I mentioned, with the tectonic activity in this area, we have quite a lot of fault zones, which result in unstable ground masses. So groundwater, ground gas, and fault zones were mitigated through the use of ground investigation and forward probing. So I'm going to talk a little bit more about my role now in the project and the key kind of points of what a geologist would do within the remit. So my primary function was to link observations of ground conditions from the tunnel and link them back to the design team and into the daily review meetings. And then also supervising excavation of material and witnessing kind of adding support installations. And then comparing the ground conditions against the design assumptions that were made. So this was mainly in rock mass characterization. So to begin our process, we would start from the TBM tunnel, as you can see in the biggest picture on the right-hand side. And we would look to do forward probing from this tunnel. And this represented the most local, finest scale of ground investigation. So the model started off with much more regional ground investigation, coming down through the TBM, and then into this stage where we're really probing the ground in which we're going to be excavating. So you can see on the blue diagram, which is the bottom left one, you can see the kind of porcupining probes. This gives us forewarning of any oncoming hazards that we might be expecting. So looking back at the ground gas, groundwater, unexpected ground conditions. So once we were a bit more familiar with what we were going through, we could do full excavation. So in this phase of works, we'd be looking at, we had the 6 adits altogether, and each one had 50 advances of excavation, removing around 800 metres cubed of rock per adit. When we were doing an excavation, Giles would be on site and look at characterising the rock mass and giving it an RMR value. To produce the RMR value, we would estimate UCS by Schmidt hammers, look at RQD, and then the condition, spacing, and orientation of discontinuities. It's worth noting that we were looking at this in 3D space, so we have the leading face, which is the centre of that slide, the crown above, and then the left and right flanks. And it's worth thinking about the fact that discontinuity might be stable in one orientation, but unstable in the other one. So we had to look at it in that kind of way. We would look at something like this, register any ground gas, groundwater, and instability, and then relate that back to how we would progress with support measures and things like this. So once we'd given our RMR and then fed that back to the daily review meeting, there might be changes or enhancements to the support measures. We would look at then selecting support, so we'd had different anchors available to us, and then we would look at management of groundwater and ground gas, so where there was an intersection of these things, we could compare it back to the ground model to understand its potential source and if we could expect more or less of it coming through, and look at how we could maybe potentially mitigate these things. We'd also perform inspection testing of our ground anchors to ground truth the design and ensure that it was operational to the desired standards. So, in conclusion, I've given an overview of the importance of geological insight to nuclear development and the importance of understanding a full ground model of your site before we begin with this kind of engineering. I think the 4 key areas in which ground engineering and geological context is important is in safety, economy, project agility, and resilience. Safety during construction, in which we have to keep our workforce safe, but also in operation. These tunnels are vital to cooling the nuclear reactors and therefore they're imperative to the design of the structures. We have economy. As I was working in temporary works, we could optimize our use of shotcrete and anchors, in which to the ground conditions, of course, which then had a time and budget kind of enhancement. We then have project agility, so being able to understand which kind of hazards may be present, we could adapt toolbox measures to combat this and avoid redesigns and being surprised by these things. And then in resilience, finally we produced structures that were suitable for the ground conditions in which they exist, and hopefully will operate for the entire lifetime of the project going forward. So thank you very much for listening. I hope you all have a great evening.
Well done, Chris. That was great. Really good. We, the committee obviously have seen the talk before, but we absolutely loved it and loved it second time round. So well done. Really good. So next, I'd like to invite Professor Jim Griffiths up to talk to give our introduction for our Glossop lecture. Jim.
Thanks for the applause, but I'm only going to be on a short while. So honoured guests, colleagues, friends, welcome. The inaugural Glossop Medal Lecture was delivered by the incomparable Peter Fuchs in 1996, and that was initiated during John Charman's tenure as the Engineering Group Chair. I was on the committee with David Shilston at the time, and he was given the task of defining the attributes needed for a Glossop medalist. David stated that we were looking for engineering geologists who had advanced the discipline through teaching, research, practice, and professional standards. And in classic David fashion, he summarised it perfectly when he said to the committee that we're looking for heroes. Today's lecture is presented by Dr. David Giles, who embodies those qualities. Dr. Giles completed his degree in engineering geology and geotechnics from Portsmouth University in 1983. For the next 8 years, his career included roles at Scott Pickford and Associates, the British Geological Survey, and Mott MacDonald, where he applied computing to geological challenges. In 1991, he returned to Portsmouth University as a lecturer to teach, train, and inspire future generations of engineering geologists. There, he completed his PhD in computer modelling and analysis in engineering geology, and also developed his expertise in remote sensing, geological modelling, and GIS. After leaving Portsmouth in 2019, Dr. Giles joined Card Geotechnics Limited, initially as a consultant and then technical director, and in 2025 became a senior consultant at the Geotechnical Consulting Group. Now, that alone is an excellent track record. But in addition, Dr. Giles has spent his career supporting professional standards at the Geological Society, notably with the Engineering Group, but also through the Quaternary Research Association. He has served as chair of the Engineering Group, been a trustee of the Geological Society, led the Geohazards in the UK Working Party, contributed to the Glacial and Periglacial Working Party, helped organise the IAG Congress held in Nottingham in 2006, served as secretary to the IAG Commission 22, and he's published extensively. However, his most enduring contribution is his long-standing leadership of the Engineering Group's annual field course, reflecting his belief that engineering geology is fundamentally a field science. Therefore, I have the privilege of introducing the 25th Glossop medalist, my old friend, Dr. David Giles, who, in a subtle reference to the engineering genius of the ancient Romans, will be presenting his talk entitled, "What Has the Quaternary Ever Done for Us?"
So I've always wanted to say this, welcome to Gardener's World. So we're going to have an evening of the bit of geology that's kind of snubbed and not taken as true geology, but hopefully tonight we can give you an insight into the importance of the Quaternary for the engineering geologist and the geotechnical engineer, understand a little bit more about its legacy, and really trying, I think, this doesn't sound too freaky, change your mindset as to how you go from solid geology, bedrock geology, and to look at the superficial deposits, because we'll hopefully see that the superficials are anything but superficial. They are critical to our engineering understanding and our developments and engineering construction within those particular environments. So hopefully I'm going to show you tonight how to break a little bit of the orthodoxies, trying to get you thinking about the deposits when they come at you through cores and logs and boreholes, and start to actually question what you're actually looking at and get a perspective on effectively the influence that the Quaternary has left and the legacy that it's left within the ground conditions. I should say that it's quite difficult. Both these screens are beyond my focal length, so if I start to move around occasionally, I'm not actually doing a runner. I'm actually trying to focus on the screens, so hopefully this works. So it's been interesting in the lead up to this about talking to various engineering geologists, geotechnical engineers about the Quaternary, and it's been quite noticeable that perhaps what some of us take for granted about that Quaternary background, the Quaternary science, is not really there. And I think what I hopefully will demonstrate is that some of that scientific and climatic subtlety is really important for engineering geology. It's really important for understanding the geotechnical profile within the ground. It's really important for understanding what hidden hazards, and I love saying this, problematic soils are actually lurking in those particular horizons. So we're going to look a little bit more about the background of the Quaternary, look at its geotechnical and engineering significance, start to look about how we plan our conceptual models, how we plan our ground investigations, how we actually start to actually go and look at those environments, and really finish off too with something that was perhaps a subject that was talked about 20, 30 years ago in terms of neotectonics, but now has a new twist in terms of some of the major infrastructure, particularly the nuclear power stations, and how the Quaternary is a really quite dynamic geological environment. It's not a static, dead environment like some perhaps of our more solid stratigraphic horizons. What lessons can we learn from the Quaternary that we need to implement now in some of these major construction projects? So I've changed the title now from what has the Quaternary ever done for us to what has the Quaternary done to us. And hopefully we can go through and see some of the case studies where we've had these problematic ground conditions. I had a lovely conversation with Rodney Bridle, about the days of dam engineering. And the dam engineers had this term called treacherous ground. And I felt that was actually more appropriate. You may just guess that I did this slide on Halloween. So hence the menace that is the Quaternary, something that we need to approach our ground investigations, approach our conceptual models of really understanding that these ground conditions are highly variable and can kick an engineering project, a construction project in the teeth if you don't understand that variability. So we're going to have a little look at the Quaternary climatic legacy and particularly understand those geotechnical, those ground engineering implications that those climatic changes, those significant climatic changes have actually presented. So this is the gardening. There's Nige and his faithful companion Monty. This is why we get sort of a bit sneered at by the hardcore geologists. So we've got 4.2 billion years of Earth history. The Quaternary is the last 2.6 million years. But really, in terms of our engineering significance, it's the last 24,000 years that have really churned up that ground, given us deposits, given us geological hazards. So in terms of that whole spectrum of the stratigraphy, we're the unwanted uncle at the party in terms of the geological column. And we're right sort of at the very, very top. But what we all do in our day-to-day jobs, it really is that, if you like, that most significant part of that geological column. Which is ironic, really, because if you think back to all your university courses, your masters, your undergraduate courses, it's perhaps the element of that stratigraphic column that's least focused upon. Yet when we actually go out and start to work, we start to see that it's probably the most important that we need to understand if we're going to de-risk projects, if we're going to have successful engineering constructions. I was told by the master's students at Portsmouth that I was the riddler. So there's your first riddle there. Where's the Quaternary legacy? If you look at the stratigraphic distribution of rocks across the British Isles, where are those Quaternary deposits? Where are those Quaternary land systems? And of course, it's a trick question because every single part of the country, top to bottom, John O'Groats to Land's End, has had a Quaternary influence. The climatic changes have left a legacy within that ground profile. So wherever we're engineering, whether it's in Shetland or whether it's in Penzance, we're going to have some legacy of those major climatic changes that have influenced those ground conditions, that have given us that treacherous ground, given us those problematic horizons. So we can't escape the Quaternary as a geological interval, as a series of legacies that are left behind. So really what I want to set out to achieve tonight is to kind of change your ground model mindset. We spent a lot of time really over the last 20 years of getting conceptual ground models to be the bread and butter of engineering geology, understanding that if we can appreciate what is in a particular geological environment, we can go and investigate it, we can de-risk it. But we've got to slightly change our mindset when we're actually looking at the Quaternary because we've got different aspects that have influenced those particular ground conditions. We've got geotechnical implications as well as geological implications. So we really need to understand some of those scientific fundamentals because there is a legacy that we need to appreciate when we're starting to develop those ground models. And I'll show you what I mean, how we can move from perhaps some conventional ground models and give you some takeaways really that you can start to actually appreciate that variability and that legacy that's actually within those particular horizons. So the other thing we need to start to dispelling is some of the kind of, if you like, the orthodoxies. This is perhaps the layperson's idea of the Ice Age. We've tended to talk about the Quaternary as the, in singular, Ice Age. And there's this static picture here, this nice diagrams really of northern hemisphere, southern hemisphere ice sheets developing, valley glaciers developing, a permafrost tundra in front of those ice advances. And we seem to think of this as like this static picture, nothing really to see. But when we actually start to delve in to those climatic changes, we've got a whole variety of different conditions that we need to appreciate. We have the glacial conditions, when it gets cold, we see ice sheets advance. We then have non-glacial conditions when those ice sheets retreat. Within those cold conditions, we have stadials when it gets a lot colder, and interstadials when it gets a lot warmer. So we're starting to see fluctuations in climate, fluctuations in temperature, which means that static picture is completely wrong. We're seeing advances and retreats, advances and retreats. As we advance, we get isostatic depression, we get sea level rise, sea level fall, we then get retreats, we get recovery. We've got this complete cycle of cold, warm, and very warm. All of this influencing the ground profile, all of this having effectively a legacy in those geotechnical conditions. And what's the enemy of geotechnics? The enemy of geotechnics is water. And this is a system that's got an awful lot of water. What happens when water freezes? It expands. We get all sorts of modification of that ground profile. So we've got these temperature variations that we then need to understand in terms of that legacy, in terms of that particular ground profile. And just to give you an example of those fluctuations, on the bottom left there, we can see the last glacial maximum that occurred in the Devensian, but we also have these interglacial cycles with the Ipswichian. And we actually do have lines in Trafalgar Square. We have the dots you can see on the map, which I'm squinting to see, are hippopotamus remains across the country. So we've gone into savanna conditions. We don't think of the Quaternary of actually having warm conditions. There's some research that suggests that on the Scilly Isles, there were subtropical conditions. So we think of that in terms of a weathering profile, in terms of that ground modification from one extreme to the other. We've got some significant influences to appreciate, again, getting to that mindset about that top surface legacy. Now, I think this was the most fantastic exam question you could set, and we've never sort of pushed our importance, but this is the geotechnical implications of Earth's interstellar position. So what's driving this is these Milankovitch cycles. So that's a Serbian mathematician called Milankovitch on the bottom left there, and that was James Kroll, who was the janitor in Edinburgh University, who also added into these models to understand where Earth's position was in relation to orbiting the sun. We have an eccentricity, we have an obliquity, we have a precession. So we're at different positions in terms of that orbit that's giving us these climatic changes. And when we start to actually plot those climatic changes, we can start to see we've got these great swings across a very, very short period of geological time that, again, are constantly modifying that particular ground profile. And even if we go into more historical times, we can again see some of those fluctuations. We had what was termed the medieval warm period. Between 950 AD to about 1250, we had significantly warmer temperatures in the country. We were a wine exporter to France during that period. So again, what's that mean in terms of the ground profile? We're starting to see desiccation. We're starting to see moisture conditions change. And then that was followed by a very, very wet and very, very cold period where we had the Little Ice Age. We got the frost fares on the Thames. Many of our landslides we can actually date to being triggered in that particular period. So we've got these macro climatic changes and smaller cyclic changes again, all having an influence, all actually affecting that particular ground profile. So we need to start thinking about moving away from this orthodox picture. This is perhaps why some of the diagrams we see are perhaps not really helpful in terms of understanding that legacy. This is the static picture. This is effectively the maximum extent of those northern hemisphere ice sheets. We've got lines on a map. We've got solid lines, not dashed lines that we've been putting on a map. What we need to start to think about are these lines really helpful? Have we got these finite lines? Is this really helpful in the development of understanding usable conceptual models? We tend to look at lithological boundaries and think that particular strata finishes there, that particular strata starts there. The diagrams that you can see there are just simply indications of a potential maximum event. They are not definitive in terms of where the modification of that ground profile has actually taken place. But they're a good starting point to start to understand about the climatic influences that we see across the country. And it's a very, very useful map in the middle there where we can start to understand where we've had glacial conditions, where we've had periglacial permafrost conditions, and where we've had a mixture of both. We can start to build up that understanding of those climatic influences and start to appreciate that we haven't got, if you like, solid lines, fixed lines. We've got fuzzy zones that we need to start to appreciate. We've got this much more dynamic picture of ice advancing, ice retreating, ice advancing, and ice retreating. So the question is, how do we incorporate that variability into a conceptual ground model to fully predict the kinds of ground conditions that we could come across in an investigation or within a construction project. So here's our typical ground models. These are our fantastic Fuchsian models that we can start with, effectively an I spy. What can you see in a particular given terrain? There's an example there of a valley glacier system, a lowland periglacial system, so we could have them for our glacial and periglacial systems. We can also develop them. These are from Julian Merton. We can develop them in our periglacial systems. And we found these very, very useful in terms of undergraduate fieldwork, for example. The bottom diagram, we can go out into a chalk terrain. Can you see these particular features? This is what we've started to entrain in our conceptual ground models, in our conceptual geological models. One very, very useful, and hopefully I can give you some sort of key go-to papers here. This is a paper by Booth, Merritt, and Jim Rose, when we started to look at the concept of provinces and domains and land systems. This effectively looks at the glacial influences and the periglacial influences, whether they be upland or lowland influences across the country. And this is an extremely good starting point in that kind of I spy ground conditions, I spy landforms, I spy deposits kind of mindset as you start to develop that conceptual model. What is the expectation in that particular environment given those climatic variations? But I want to sort of change that a little bit and sort of give you another kind of twist on that. I once went to a very interesting public lecture which was given by Professor Sir Roger Penrose. And he worked with Stephen Hawking at Cambridge and Dennis Sharma. And he gave a presentation on the origin of the universe. And he used 3 overhead transparencies. And the first transparency was saying, I was Sir Roger Penrose. So I'm going to give you, hopefully not in the same caliber as Sir Roger Penrose, but I'm going to give you 3 slides here, which really to get you into that mindset. And this is the first one, really. This is a most fantastic photograph from Dave Evans from Durham of a modern-day ice margin in Iceland. And I'm not even going to pretend I can start to pronounce that even from this distance. And this picture, I think, alone, for engineering, geology, and geotechnics, is something to start to more fully appreciate of what is the legacy in a glaciated terrain. Because when you actually look at that valley glacier, you've got a whole load of land systems, a whole load of depositional environments that are presented by that ice front there. You have a proglacial ice front, you have a glacial lake, you have subglacial sedimentation, you have superglacial sedimentation, you have outwash in a glacial fluvial environment, you even have shunted material in terms of a glaciotectonic environment. So over a very, very short distance, you've got a lot of variability in the deposits, a lot of variability in the geotechnical materials that are there. You've got a lot of inherent geological hazards that are lurking in there. You're planning your site investigation. How many boreholes do you now need to characterize the legacy of that environment? You would go and put pinpoints across there. Would you be able to join the dots? There's no dot joining there at all. Conceptually, it's a variability that needs to be into your mind. These ice marginal systems become really quite significant. Now, when we first started engaging with the engineering group, with the QRA, the Quaternary Research Association, working on Engineering Geology Special Publication number 28, when we started looking at these, we were a bit poo-hooey about what these are, the marine isotope curves. Effectively, this was seen as a kind of research element. They were effectively showing that, okay, climate had changed with the Milankovitch cycles. What on earth has really got that, has that got to do with geotechnics? But the more we then focused on these particular curves, the more you realize this is what was influencing that ground profile. We needed to understand about how the climate changed, the frequency of that change, and that legacy that was actually provided. So the curves then became important because we had some very, very old glaciations, which are the first time it incorporated bedrock into glaciogenic materials. But subsequent glaciations, subsequent ice advances, completely reworked and remolded that material, gave us a different geotechnical characterization of those ground conditions. So these fluctuations, understanding that we didn't have a static picture, we had a dynamic picture, became very, very important in, again, developing that mindset, developing that we've got variability, we've got reworking, constant lateral and vertical change. And I hope this works. This was some very brilliant work done by, starting with the University of Aberystwyth, Sheffield University, Durham University. Part of what was called the BritIce project. and starting to look at that variability and start to reconstruct ice margins. And there's a little video here. Luckily, we've turned the soundtrack off. The soundtrack's a bit cheesy. If I press the button, it should work. So this is the last 35,000 years to 38,000 years to 10,000 years ago. And they modeled these climatic variations. They modeled ice advances, ice retreats. The scale there is meters per year. And you start to see now, effectively, what is happening to your ground profile. This extremely short period of geological time, this constant reworking, this constant remolding, this constant incorporation of new material into old material, giving your geotechnical layer, giving your foundation layer, giving your investigation layer. And the legacy of the variability, both lateral and vertical, becomes an important point in that mindset development. We've not got this static picture. We've got a highly dynamic picture, highly dynamic reworking of that particular terrain. And sometimes it's very difficult to sort of break away from, because we like static things. We're used to understanding about the London clay formation as a nice static horizon, give or take. We understand the chalk, give or take. The Mercia mudstone, give or take, is relatively static. Here we've got massive inherent variability because of these dynamic processes in this very, very recent part of geological time. So if we're going to inform the ground model, this quaternary history then becomes really quite important. Some of these fundamentals of quaternary science, understanding the climatic variations, what does that mean in terms of the glacial and periglacial genesis of the materials that we're looking at? Have we got these primary tills where bedrock has for the first time been incorporated into an ice advance, or have we got reworking? The nature of that ice advancing over the substrate. Have we got passive or active transport? Have we got material that's being ground down into a fine-grained mass? Have we got larger clasts that have been carried along on the top of the ice, for example? Have we got direct bedrock inclusion? Have we got reworking or remolding actually taking place? So that whole ice process gives us our engineering and geohazard significance. Those mechanical processes become significant in the understanding, in the mindset development when working in these terrains. We've perhaps not got deep basin sedimentation or a desert environment which is spatially very, very extensive and spatially very, very continuous. Here we've got this continual variability, this continual lateral and vertical variation. And that's the legacy, really. We're not going to read them all out, but this starts to become the geotechnical legacy. We've got anisotropy, we've got different environments, we've got water, we've got land, we've got shunting in terms of tectonism, we've got constant reworking, we've got constant lateral and vertical variability, and each of these then has a geotechnical implication that we need to appreciate. And I think that appreciation of the lateral and vertical variability is the kind of key message. We tend to not look at scale. We tend to not think of things varying over very, very short distances. We tend to not think about those, if you like, those things we were taught as geologists. What was those primary environments of deposition? We need to understand those different depositional environments because we get different geotechnical properties. We get different geohazards. So whether we're looking at primary ice, we're looking at meltwater, we're looking at a lake deposit, we're looking at a bulldozing, or even if we're now going into the marine environment, all of those depositional environments are going to give us a different legacy. And again, we were all taught this as undergraduates. The present is the key to the past, from Charles Lyell. And I think of all the geological ages of all that stratigraphic column, this is one part geological time, the 2.6 million years, where that becomes extremely important. We can go to Iceland, we can go to the tundra in Canada and see these current contemporary environments to understand what that means in terms of the relic conditions that we encounter in the UK. So we're getting geotechnical materials. We've got security on standby for certain of you. If anyone says the word in the middle, which some of you know from many years is not allowed. But we need to again move away from thinking of glacial tills as one material. All of these, you might say, could be described as a glaciogenic material, as a glacial till. But some are deposited subglacially, some of them are carried on top of the ice, they're deposited superglacially, some are shunted along, some are tectonized. And so that one word till, perhaps, as we need to sort of subdivide further, because as you can imagine, looking at the images there, each of those images has a different geotechnical response. It has a different aspect, a different hazard that it will present in terms of ground profile. We have over-consolidated fissured clays. We have poorly sorted angular cobbles and boulders with a fine-grained matrix. We have a boudinage developing there because we've got glaciotectonism. And my favourite one on the bottom right there, that is a deposit. Those are the chalk rafts that the ice has gone across the chalk substrate in the North Sea, ripped up enormous lumps of chalk and then stacked them on top of each other. When we're starting to look at the offshore world now, that becomes an extremely important aspect of planning a ground investigation. Never trust a hole offshore chroma that says it's in chalk. Make sure you go deeper, because you can go through the bottom of one of these into another glaciogenic material before you can then go into the chalk again. And you imagine what that structure on the bottom right there starts to behave when it's actually loaded. So again, it's a legacy of this material variability, not a single material, but multiple aspects of that depending on where those deposits were formed in that advancing and retreating ice sheet. So in this system, the ice marginal system then becomes really important. This is perhaps the most dynamic of those particular environments. We have this lateral, vertical variability, we have material variability, we have geotechnical variability. And again, when you actually look at that lovely slide there, where would you plan an investigation? I think I've got another example there. We've now moved offshore, and that's our environment we're actually starting to investigate for our wind farms. And we seem to have forgotten that the sea level recovery is only very, very recently in terms of quaternary times. But now at the moment, we've got many investigations, many seismic surveys, offshore CPT surveys taking place in that particular environment. And for example, we've got east-west rails going to be effectively traversing across an ice front going from Oxford to Cambridge. We've got many of our monopiles. But if you actually think about that, about how you would plan that as an investigation without getting into the mindset of a quaternary conceptual model, you could come really quite unstuck. Across that whole scenario there, we have these differing geotechnical parameters, differing ground conditions on a very, very small scale. Sometimes on a 10, 20 meter scale, we're seeing that kinds of variability. So our mindset when we're actually interpreting the data is a move away from perhaps where we are in conventional, if you like, solid or bedrock geology. So I was going to give you, had to sort of protect the innocent on a few of these, but I'll give you a little examples of what happens when you actually don't fully understand that variability in those environments. This was a brand new school that was built in Hertfordshire, and the school was built, and very quickly they had groundwater flooding issues. They had groundwater flooding issues because they built the school effectively on a buried glacial fluvial system. The ground investigation had not fully understood what was the legacy, the present is the key to the past, with a whole series of stacked and buried channels. So the construction had taken place, the ground model hadn't been fully appreciated, and effectively there was this complete hydrogeological continuity through these relic glacial fluvial channels. Another example, this is Bishop Stortford Station Yard. New construction then taking place, starting to put in place piles. This is the River Stort. The River Stort was a major drainage channel coming off of the Anglian ice front. You can imagine what happens when an ice sheet starts to wane. The energy in the system, the downcutting, the sediment that's being emanated from that system rapidly fills up a very, very deep valley. And the land system that was present there was a series of channels, abandoned channels, and abandoned ponds. So every time we did a CPT across that car park, we got a completely different trace. Every time a borehole was put in place, there was no lateral continuity because you had this braided system, isolated ponds, small lakes, each with different sediments actually within, each giving different ground responses in terms of the geotechnical profile. Another example, this was a new retaining wall that was cut into the supposed London clay in North London, started to get a significant deflection on that wall, and the environment was effectively the relic periglacial environment. Flows and active layer detachment slides, giving a whole variety of remolded material, of sheared material, and there's the construction effectively on that paleo legacy environment of not fully understanding it. And this is where testing the orthodoxy comes in. This was the area of the classic Skempton brown clay, the weathered profile within the London clay. How do you test whether it's a weathered profile, so you have a reduced strength, or it's completely remolded because it's part of the solar fluxion flow and active layer detachment slide processes? And this is now where the smallest of evidence, when we're starting to log and describe these materials, can then become very important. I don't know if you can see in the middle of that brown clay, there is a nice rounded clast that's actually present there. And that is a clast from the Dollis Hill gravel. That is the terrace gravels that sit on top of the London clay in the London basin. So what you're looking at there is completely reworked material that's incorporated a single clast that's managed to entrain itself within that material. That's important geotechnically because that is now fully remolded. That has a residual strength as opposed to part of the brown clay, the classic brown grey clay in the London clay formation, which is part of the weathering. So extremely small pieces of information can sometimes help unlock that ground model. And those of you who are more geotechnical engineering focused in the audience know the significance of changing that value in terms of your design calculations. And I couldn't do a presentation without talking about these particular features. This is perhaps the worst kept secret in all of engineering geology. This was the new American embassy in Nine Elms in Battersea, and they were constructed on top of a former periglacial environment where there was a significant drift-filled hollow. And there's still a very, very lively discussion about whether we're looking at relic pingos, these ice blisters that have left a significant foundation legacy. And if you're working in London, this should be a key aspect of your conceptual models if you're working in London, the nature, the distribution, and the impact of some of these drift-filled hollows. This few years ago, we had Eddie Bromhead's Glossop lecture where he talked to us about slide-prone horizons. He focused on landslides and looking at what were key and critical problematic layers within a landslide system that perhaps had been overlooked in the past that then can control that kind of slope instability, and very much focusing on volcanic ash layers, sources of smectites, giving us very, very thin yet highly significant layers in terms of controlling ground instability. And the same goes in terms of the quaternary environment. We need to understand where is the treacherous ground, where are our problematic layers that are going to give rise to slope failures, embankment failures, and how do we find them in a ground investigation? Do we go looking at them in a conventional ground investigation, or do we need to change our mindset into how we go and undertake those intrusive GIs? We can give lots and lots of examples. We can spend entire lectures really looking at some of these key problematic layers. These are perhaps, give you an example of two of the perhaps most critical that we've started to develop our understanding in engineering geology and geotechnics. This was the A21 Seven Oaks bypass in 1965, where there were major slope failures, and perhaps for the first time we started to understand the significance of that periglacial legacy, where we had reworked material giving us effectively flows with lithic relics in a clay matrix. We also had active layer detachment slides where we had significant shear surfaces. And again, we can go and look at the Carsington Dam failure in 1984, where the classic yellow clay horizon was actually present. This is extremely significant in some of the new reservoirs that are being constructed or investigated across the country at the moment. You know, putting very, very large embankments on top of the periglacial legacy in terms of the ground profile. What do we need to understand about the significance of those problematic layers, of that treacherous ground? How can we then go and investigate? How can we ascertain that we've de-risked that they're actually not present, or find them and then deal with them if they actually are present within that ground profile? So I'm going to have a little look now at sort of some case studies where we can start to think about these critical layers, these, if you like, failure-prone horizons, how we can start to investigate for them, how we can start to understand their presence. And we can really go back to some fundamentals of understanding the depositional model, how we start to bring back stratigraphy, high resolution stratigraphy, when we're starting to develop our conceptual models and de-risk the particular projects. And perhaps think about differing ground investigation techniques we can use to find these subtle layers that are present within our ground profile. So we've got a couple of case studies really of showing the glaciolacustrine environment, the glacial lake environment. And this is an example in a place called Varon. Those of you who follow the Tour de France, some of these will be very, very familiar. where we had, there was a project where in the center picture there is the TGV crossing, and they actually had a level crossing on the TGV, and a gentleman in his French lorry got caught on that TGV crossing, and there was rather a large incident, and it was decided then to put an underpass to actually create a much more safer crossing. And so an excavation started, the engineers came along, and as many engineers love to do, banged a load of sheet piles into the ground. And you might see in the center there that the first clue really is the laminated nature of the deposit. And this is the legacy of that glacial lake, that glaciolacustrine environment. And what happens when you start to bash it with a sheet pile, you start to liquefy it. So we start to see on the right-hand side there, you can start to see a lot of moisture being released within that ground profile. So not only was it the important TGV line and starting to see closure within that cutting, the building on the right there, some of you may remember very, very fondly, is one of France's national monuments, which is the Chartreuse distillery. So it's been around since the 1400s, and the cutting started then to close in because the glacial lake deposits started to release their interstitial water because they were not understood and they were not treated sensitively, which will be a comment in a moment. Luckily, they managed to actually save it, so there's the 250th anniversary in 2014, and the Chartreuse distillery was saved. But you can start to see that if you don't understand the nature of those materials, very, very quickly you can start to realize a risk, start to realize that geotechnical hazard in terms of the disturbance to those particular materials. Now, another example is the A51 construction. The A51 was a very important route. There was, those of you who are aware that the French go on holiday on the 1st of August in Paris. The entire city goes on vacation. And there's a website that has the world's longest traffic jams. So someone somewhere has got to do it. And on the 1st of August, there was a 110-kilometer traffic jam of the Parisians trying to get down to Provence. So this became a very, very important route in actually de-stressing that Rhone corridor, effectively going from Grenoble down to Sisteron in the south. The difficulty was the road was actually crossing through this ice marginal landscape, crossing through an area of significant glacial lakes. Part of the road was then constructed. You could pay €1 to go on effectively the section you see there. Effectively half a mile later, you came to a small roundabout on what was effectively a B road. So for 35 years, there was nothing in between connecting the two systems. It was going through this highly challenging quaternary area, a glacial and ice marginal environment, an area with major glacial land systems. It was also had challenging geological conditions because it was a seismically active area, and it gave rise to a whole variety of problematic soils. So this was the paleogeography that helped to then unpick and understand and start to focus again on those, if you like, those failure-prone horizons. You can see there effectively a reconstruction of the major valley glacier systems, the Isère, the Romanche, many of the sort of the existing ski resorts, the high elevation ski resorts. And on the left-hand side there, you can start to see the sedimentary legacy, the sedimentary deposits that are left behind within this glacial lake system. But as we start to have a look in a moment, all is not what it sees. We can see quite what looks like a relatively competent set of deposits, but they have significant geotechnical issues. So back to our original, if you like, baseline geology, understanding the depositional environment. There's effectively the conceptual model of the depositional environment for a valley glacier with an ice marginal lake, starting to see deposits and the variety of deposits that we can start to find in that particular lake setting. We can see ice rafted debris. We can see the classic rhythmites, or if you like, old school geography, varves, couplets of silts and clay. And in the deeper part of the lake there, some quite remarkable photographs. They're actually turbidites. They're the scours, the scour toe features with turbidites running down into the depths of that glacial lake. So we've got a lot of sedimentary variability there, but there lies the geotechnical hazard. Within these clay and silt couplets, we've got significant amount of interstitial water is actually held within them, trapped within them. But as we saw back to the Chartreuse cutting, if you start to disturb that, you can then start to actually release that interstitial water and start to see a liquefying process then start to take place. And to give you an example of how problematic that can be, this is the Synard sector. This is the area that the road was going to be constructed through. And you start to see how there's a major landslide systems then start to develop. On the right-hand side there, you can see that it starts as effectively as a rotational failure, that then becomes a translational failure. And then as this water is then released, we see mud flows. We see significant mud flows. And these have actually caused a large number of fatalities in this particular part of France. They are high velocity, extremely problematic, and obviously in terms of being caught in one, they are extremely dangerous. But we see this change from what looks like quite competent strata into effectively completely liquefied, and significant mud flows then start to generate. But all is not what it seems. We're sort of thinking that we've got these great thicknesses of these glacial lake deposits, but when we start to actually focus in, we can see that we've effectively got these laminates holding the water, and in between them we've got much more over-consolidated, clast-rich material. And this is representing these advances and retreats of the ice front. And when we start to actually log the outcrop, we can see that the controlling horizons are these very, very thin bands of these glaciolac deposits. The mass as a whole is not really the answer. It's these very, very centimetre scale bands that are actually controlling that stability, that are releasing that water, that are then creating these large scale rotational and translational landslides. So the subtleties there, back to Eddie Bromhead's slide-prone horizons, the significance of these individual layers becomes again important in our ground investigation. So the project, just to give you sort of how the project was then completed, they actually started to construct the major infrastructure, the tunnels, beautiful viaduct, but the roads connecting the tunnels, the roads connecting the viaduct were effectively left unbuilt. So it was going through a lot of contractual and risk transfer negotiations. In the end, it was a Scottish company that actually took the risk and then started to come up with the engineered solution, which was a whole series of extremely wide basal embankments, effectively building up and distributing very, very carefully the load across those sensitive deposits. There was even liming was then taking place as well to experiment in controlling some of the water. So the road was then completed, and the road was then completed a significant time after some of these initial bits of infrastructure. The tunnel was completely completed, and there was no road connecting the tunnel. You could walk through the tunnel onto the viaduct, but there was actually no road actually completing it. So that was our French examples. We've had the same issues here. This was the second Tyne crossing. That's one of the engineering group field meetings actually going into the immersed tube tunnel. And this is the famous T-side laminated clays. You can again see the laminations. And again, in the photograph in the bottom center, you could start to see it starting to remold. It's starting to actually get a bit gloopy as this water is then started to release. And so it's important, again, in perhaps the second desk study takeaway, is that when we start to look at these paleogeographies, this is a legacy environment that we have across considerable parts of the UK. This is a great paper by Della and Julian Merton that sort of looked at the lake reconstructions where you might find these sensitive and slide-prone horizons. So again, as another key desk study paper, this is very, very useful in delivering those change of mindsets in those conceptual ground models of where you might find those particular deposits. So let's have a little look about what we might do then in terms of how do we actually go and undertake a ground investigation for those delicate and sensitive soils. So there's our equipment we've got for knocking the hell out of our delicate, sensitive soils. We can bash it, we can dig it, we can trample on it, putting a lot of energy into there and effectively getting a bit of a nasty surprise when we get a bucket of mush back, and then we try and actually sort of reconstruct what we're actually looking at. So we perhaps need a different mindset in terms of traditional and conventional ground investigation of what we can then start to utilize to actually profile that critical ground profile, highlight those problematic horizons that can help us understand the hazard and then subsequently de-risk them within that profile. So we've got these subtle geohazards, we've got these problematic horizons, we've got these shear zones. We need to think about how we actually go onto site to record them. We found it very, very useful that being on site as literally as the material comes out of the ground, splitting the cores, we can start to see aspects of those shear surfaces, the relic shear surfaces, But then coming back again, when those cores have started to desiccate a bit, how are they separating across what are effectively desiccation cracks, drilling-induced cracks, or are they separating across failure zones? So if you're in a cohesive deposit that's in experienced periglacial conditions and you're actively looking for shears, you might like to have two logging phases, effectively the live logging as it comes out the ground and then returning. Remember back to the London example, we want to differentiate between what is effectively a weathered horizon, what is in situ, and then what is actually a remolded horizon. So we perhaps need to think about how we time our logging, how we actually go back and look for these subtle geohazards. Now, I've started to see it I had to actually ask when they first saw them, and it's perhaps really, it was ignorance really. We started to see a lot of AZCL on logs, a zone of core loss. And it started to become apparent that, when we were doing bish bash bosh in these sensitive soils, the bits that weren't coming back were screaming at us because they were the key pieces of information. Sometimes think that perhaps the zone of core loss is perhaps the most critical of the horizons because it's telling us that's a weak zone. It wasn't strong enough to be recovered by the particular ground investigation technique, and it's starting to show where we have these failure-prone horizons, whether it be on an embankment or on a slope. So perhaps we need to sort of pay a little bit more focus when we start to see that on a log, and again, the change in the mindset. Rather than thinking, oh, it's not very competent drilling, it's poor quality drilling, perhaps it's telling us some much more important value-added information than perhaps we thought that we would get out of such an investigation. Now, I've started to see that one regret I had at lecturing at Portsmouth was we never really delved into cone penetration testing. And it's since I've kind of gone back and working in industry, I suddenly have become much more appreciative that this is perhaps one of the key techniques that we perhaps have overlooked in the UK in terms of these much more softer and delicate soils. I know we're now improving on that in terms of what we do offshore, but we can start to use the CPT to start to understand where we have those very, very weak horizons. And when you couple that with a sampler called the MOSTAP sampler, where instead of, again, ramming a U100 into the ground, we can use a very, very soft push and start to get some very, very delicate, sensitive soils recovered to start to perhaps understand. And this is, again, is an example from Bishop Stortford, where some very, very fine-grained gravels that had a carbonate precipitate within them. They actually had carbonate that had dropped out of the highly saturated chalk-derived water flowing through them, giving a very, very strange material that would have been completely lost if we'd have perhaps used a much more conventional technique. And so this is just to show you, it's probably one for the paper, this rather than one for the screen. This highly variable environment at where we were doing it at Bishop Stortford Station, where we had these ponds, these isolated ponds into river channels, into much more fluvial glacial material. And to show you how the MOSTAP sampler was really recovering, we actually started to recover leaf mold from within those deposits, starting to understand that we had another problematic horizon. We had organic horizons that were actually within there. So starting to load them with the piled structure, with the foundation structures, that became a critical piece of information that perhaps with a conventional technique, I mean, maybe some pushback saying, no, you might have seen it, but the subtlety of the MOSTAP sampler enabled us to fine-tune and understand, some of the idiosyncrasies of that legacy environment left behind by a lot of those stagnant ponds where there was actually finer grain sedimentation actually taking place. And I think the CPT trace, I think this is what we should all start to really appreciate a lot more. Has that subtlety within it? It's like reading the tea leaves at first. No one really tells you how to do it. And it's only by looking at a lot of these, going back to your conceptual ground models, what's the expectation, what's the variability? And on those CPT traces, there is a myriad of information that really helps understand that complexity of that environment, where you're getting a sudden loss of strength, a sudden increase in strength, the inclination changes, showing you going through more granular material, and then you're hitting bedrock where you're seeing big spikes in the pore water pressures. So I think in terms of, again, changing the mindset, understanding that the CPT can offer a great deal of value added in these highly problematic horizons. So I'd like to finish off really with sort of another quaternary impact that, as I mentioned at the beginning, I think we're only starting now to refocus on, and that's really the whole concept of neotectonics. Adrian Collins from Arups was really the champion through the sort of 80s and 90s of trying to get us to think about neotectonics. And it's something that kind of has gone out of vogue is effectively looking at the more recent movements of horizontal and vertical crustal movements, looking at faulting, and is that faulting active? Is it benign, or can those faults actually still move? And that's been sort of brought a little bit into focus with the new nuclear power stations, Wilfer there and down in Sizewell, starting to understand that bedrock faulting system, is it prone to movement? But a lot of the focus there has been on actually dating the paleo movement by looking at the fault gouge rather than putting it in a quaternary context. There's loads of evidence about quaternary sea level rise with raised beaches, etc. What we need to know is how often are these faults moving? Are they still moving? And we can start to see that there's other data sets now that can help inform whether we've got much more active movements taking place, which you can imagine in terms of the risk for the nuclear power station is quite important. You know, it's sat on top of a fault that starts shifting around. That's going to have a significance in terms of that structure. Now, we can go back to Mike de Freitas' Glossop lecture, where he presented the whole aspect of faulting in London. We've got some very interesting aspects of the river system in London, which does some strange 90-degree bends. When we start to actually look at those bends, we can start to think that's the river that's hitting a fault that's being diverted. And reconstructing that, we find very interesting correlations with the underlying effectively basement faulting system, the Variscan imprint that has been effectively brass rubbed into the overlying sediments. So, okay, so that's fine. London is much more heavily faulted than perhaps we thought a decade ago. And there's Tom Morgan's PhD paper there, starting to present some of the complexity of these fault zones, something that perhaps in our geological conceptual models, we've only really started to appreciate since Crossrail more recently. This was a project that I was involved in, again at Wembley, where we had, is that 6 or 7 boreholes, no joining the dots whatsoever in those boreholes. We were going through highly indicative strata in the Lambeth group and the chalk and the London clay. Strata we had a really good handle on, and trying to reconstruct that as a geological model was extremely difficult. So we've got faults all over London. So what you say, there's faults all over London. That's great. We've developed our little bit of ground model a bit further. But what if they were active? What if we still got quaternary-related movements actually taking place within those faults? What evidence might we then go and look for? And we had a project just across the road in St James's. The photograph in the bottom left-hand slide there shows you the Thames Terrace gravels faulted with the London clay underneath. That's 100,000-year-old gravel. So we've got the Shepperton gravels. On the right-hand side there, this is in full sight. This is from the BGS London memoir. Out in the east of London, we've got the, I can't remember what the gravels are called, again with a reverse fault cutting through them. So these are quaternary deposits that have got faulting within them. So all of a sudden, we've gone from, if you like, geological time to perhaps sub-geological time, where we're actually getting active movements, active displacements actually taking place. So these are not benign faults. They have moved in effectively a time window now that has the potential to affect the engineering project. Now, other links to this now become quite important, and when we start to look at some of the new data sets that are becoming available. We got very excited about the INSAR data, and guys at Imperial have worked and produced these interesting maps where effectively they're looking at a line of sight measurement. So this is a radar-based data set where you can look at a line of sight, you can get a vertical and a lateral displacement. And they started to see that over the time frame of these data sets, you started to see blocks that were moving up, blocks that were moving down, blocks that were translating against each other. And when you started to put some lines on those maps, you started to see this strike-slip pattern, this Variscan imprint. So these are real measurements now of displacements of bits of London that are bobbing up and down, bits of London that are sinking. So we're now looking at historical time. We're looking at really the last, I can't quite see it there when the earliest data was. I think the data goes back to about the 1990s. When you start to combine these data sets with these highly accurate radar images, you start to get a very, very different feel about how things are particularly moving. And that became, I got sadly excited about this. So we've been working very closely with SatSense, who are one of the key providers of this data. And they were looking at a couple of basement projects in Mayfair. they were using two different INSAR data sets, and one of the basements came up with what you might expect. You construct a large basement, you get a zone of depression, and you get this nice symmetrical zone of depression within usually the London clay formation strata as the basement is constructed. You've got a nice symmetry to that. But what then got me excited was in the same geological conditions, the same stratigraphy, one of these basement constructions gave rise to quite a significant asymmetry in terms of how that cone of depression was then starting to develop. Started to see that there was effectively a lineation that was starting to be picked up, and this data has a 6 to 12 day repeat cycle. So it's a high volume of data that's live, that's real time to the construction then taking place. We can start to see we're getting a very different displacement pattern. And I started to get a bit excited and speculate that perhaps what we were doing here, we were picking up one of these faults, and because of the depth, these basements are really quite deep, we were starting to propagate movement on one of these faults that was orientated. So it was not the ground response from the engineering construction, but behind it, backed up by some of the bigger structural pictures that INSAR provided, we have a very interesting dilemma. Is this really our engineering starting to shift the faults around? And this is the ground relaxing and accommodating that movement, and that was then picked up by the INSAR. It was not what was expected in terms of the symmetry from the cross-sectional profile. So back to Mike's De Freitas's London faulting map. Do we need to start to think about these faults that we're starting to map? Do we need to think of them in a different light in terms of that quaternary legacy? Have we got perhaps a larger geotechnical and even geological hazard problem that perhaps we thought about in the past? So again, mindset, we've got this movement. And I put this up because, we've gone through our undergraduate programs reading a textbook called The Dynamic Earth. And we think perhaps the dynamic Earth is not sort of contemporary. And this was something that Jackie Skipper mentioned, that she had an archaeologist friend, and I remember now it's Mary Ruddy, and they were working on Crossrail, and they were doing some of the archaeological digs on Crossrail, and they had a Bronze Age track that came out of what was the original city of London. And that had effectively a displacement, a lateral displacement across it. So now we're going into the Bronze Age, where we've actually got some archaeology that has been sheared effectively, potentially in one of these active fault zones. So we're starting to see very, very recent data sets that might say that, is it more historically active? What was shearing that Bronze Age track? It's not something that we would effectively leap to. So again, it's the different mindset. Have we got a larger hazard there than perhaps we've actually perceived it in the past? So final comments really are sort of the takeaways really, that ground is complex. We know that when we start to look at ground investigations, when we start to look at conceptual models, but the quaternary really is more complex because of the legacy of those recent climatic changes. We've got significant variability in those ground conditions we need to really appreciate. We don't yet have in this country a high-resolution quaternary map base. I keep teasing Holger Kessler that the Selby sheet is perhaps our best quaternary map from the BGS. The BGS have come to the party perhaps with good influences lately in terms of actually realising that mapping the quaternary is an important part of that map base. We are not taking students out into the field to look at those particular materials. We're losing that field-based education. We're losing that field-based training. The QRA and the engineering group are now starting to actually put that into practice and start to actually take early career staff out into the field to then help understand that variability, help characterize, describe, but also help to understand the impact of that variability. So just finishing off, I'd like to thank Jim and Nick for proposing and seconding. Thank you, engineering group, for what has been a tremendous honour at my time of life and to my career. It really has been fully appreciated. And really, to finish on, really a great plug. Many of you over the 25 plus years have come on to the engineering group field meetings. And I think this is the key environment where this complexity is really understood. It's all right doing it in a classroom, it's all right putting up some slides, But until you're wandering around and talking with colleagues, the great opening line on these field trips is, I have a project where, and you start to understand where you've actually seen that variability. So I'd like to thank Ron Williams. He took me and a very young Angus Maxwell on our first of our engineering group field trips. We went down to the Mumbles. We went and stayed in a hotel, a bed and breakfast hotel, where the owners were selling up. They'd gone away for the weekend, and they left the 22-year-old staff in charge of the bar. So what could possibly go wrong? So that was my introduction to ex-field trips. And again, many of you over the years have been, and I think that's something that really is an important plug, is get on the field trips, whether it's your company trips, whether it's your local group trips, or whether it's the EGS trips or the QRA trips, because really that's how you can really fully understand the complexities in these growing profiles. And lastly, get the quaternary before it gets you. So thank you very much.
As great as I thought it would be. Well done, Dave. So next, I would like to invite Nick Langdon up to give the vote of thanks. Thank you.
Well, that was quite something, wasn't it? Madam Chairperson, ladies and gentlemen, what has the quaternary ever done for us? Some of you, like me, on seeing the title of tonight's lecture, would have smiled and said to themselves, surely Dave isn't going to try and remind us of Monty Python at such an important event in the Geological Society's calendar. But knowing Dave as I do, and I think it's entirely probable he was thinking in that way. I should go on to say it's been my privilege to have worked with David for nearly 40 years. First as relatively young academics and co-researchers at the University of Portsmouth in the 90s, and more recently as a consulting engineer with CGL. His thirst for knowledge, his enthusiasm for the subject, and his ability to communicate were always clear in what he did. This was coupled with a fine sense of the ridiculous, which allowed some sanity to prevail in the face of the mindless bureaucracy in those early days in higher education. Throughout his academic life of some 30 years, he has inspired many to join this extraordinary and fulfilling profession. And I'm delighted to see some very familiar faces in the audience tonight. We should also not forget that in addition to his academic and consulting work, Dave has also been a hard-working servant of the engineering group, as Jim alluded to. And I'm sure many of us agree tonight the Society owes very much to him over the many years that he's worked for it. Thank you, Dave, for tonight's lecture. It's been a triumph of an engineering geology career, well spent in academia and consultancy. As is the gift of an experienced communicator, the complex is made to seem simple. The academic effort and inquiry is made to sound almost routine. And the importance of the message is accentuated by the occasional wry comment that keeps our attention. Let's be under no illusion. What is observed of the surface and near-surface formations of this planet is crucial to those of us working as geotechnical engineers and engineering geologists. And maybe at times in recent years, it seemed the focus of this zone, so dear to the hearts of Skempton and Fuchs and Chandler, has been blurred in favour of the rarer and perhaps arcane. Dave, tonight you've brought us back to focusing on the surface and near-surface geology, the landforms, and their impact on man's need to develop and protect this planet. You've also shed a light on the rapidly developing possibilities with remote sensing for relatively modest projects and the benefits they can bring. So what has the quaternary ever done for us? Might I suggest it's impacted our road designs, our water supply, our housing and our infrastructure, and many, many more aspects of our lives today. It's given us a common language, a vocabulary that we as professionals use to communicate with one another. Is that almost Roman, dare I say? To conclude, tonight's lecture is one that will be referred to in years to come as formative for current and future generations in our discipline. And I strongly recommend it to the society and the profession. Thank you.
Thank you, Nick. So on to the presentations. Thank you. You've done the hard work now, so you get the prize. Emma, can I invite you up to present? So Emma Slack is going to present on our medals and certificates to our winners on behalf of the Glossop family. So first of all, I would invite up Chris Spence to receive his presentation, his award for the presentation of the 2025 Early Career Glossop Award. So there we go. Well done, Chris. Excellent. And then, Dave, I'll invite you up to receive your medal from Emma. Dave, we'll just have a quick photo of you and Chris. Is that okay? Yeah, sorry, Steph. Thank you. Steph's doing an amazing job because our photographer was poorly. Well done, Steph. Brilliant.
Thank you.
Thank you. Thank you, guys. And then just a token of our thanks for Emma. Thank you very much, Emma, as always, for supporting us. So the Glossop family is an amazing support to us. So token of our thanks. Sorry about the flowers on the tube. Oh, okay. We'll have a photo together. Thank you. Yes, excellent. Thank you. Thank you very much. Okay, so that was excellent. Thank you very much. Really good to see so many people here, and it was just a brilliant talk. I really enjoyed it. So we are just going to go through a few thank yous. So first of all, though, the big news, I'm pleased to announce the next Glossop lecturer for 2026 will be Anne Williams of Becca in New Zealand. And so that's up on the screen now. So congratulations to Anne. The Glossop lecture, we're going to clap. Well done, Jackie. The Glossop lecture is going abroad next year, and we will be holding it in Delft in the Netherlands as an integrated part of the IAEG Congress. We're very happy to welcome Vasilis Marinos here tonight. He's the president of the IAEG. So welcome, Vasilis. I'm not sure where you're sitting, and please go and have a chat to Vasilis if you're here and staying around for dinner. So a reminder that you can engage with EGGS and our active early career group on LinkedIn. We'll find a quarterly newsletter, all our upcoming events, and we usually have sort of monthly evening meetings and hybrid meetings around the UK, and sometimes at lunchtimes as well, webinars at lunchtimes. Early notice of our annual conference, so it's up on the screen now. Again, back in Cambridge next year, so the 9th to the 11th of April. We've got the date already reserved. And we're looking at the engineering geology of infrastructure projects. So hopefully that's nice and broad. And we're doing that in association with the Geotechnical Asset Owners Forum. So hopefully we can help them with some of their trickier ground conditions. So finally, some thank yous to our sponsors. So thank you to Antea Group for sponsoring the award. Thank you to Mott MacDonald for sponsoring the main lecture. Thank you to Jacobs for sponsoring the audiovisual and the live stream. Thank you to our other sponsors, GCG, Coffee, GEA, Stantec and Atkins Realis. And, it's a huge job putting this lecture on, and we really could not do it without all our sponsors. So I'm really grateful to all of them on behalf of the committee. We're really grateful for that. Thank you to the staff at the Royal Institution for hosting us so well, and our audio-visual team. They've done a great job. Thank you very much. And finally, thank you to our fantastic eggs subcommittee, in particular Josh, who's sitting up there, Steph, who's here, Lily, who's here. They've done an absolutely huge amount of work to pull the event together. So thank you very much. Again, we couldn't do any of this without all our dedicated volunteers on the eggs committee. So finally, if you're having dinner, you should have one of these on your wrist. I mean, I'm sure you're all having dinner, but if you're having dinner here, you should have one of these on your wrist. So remember to collect your belongings from the cloakroom if you've left them there. If you don't have a dinner ticket, enjoy the pub. And if you do have a dinner ticket, we will see you through the doors, and the staff will point you in the right direction. So thank you very much.